in Robert H. Tremen State Park in central New York. It's one of central New York's famous gorges. So we'll be walking through and talking about how this gorge formed and why it's here. There are actually lots of gorges through central New York, and a lot of people have an idea that they have something to do with glaciers, but they don't really have a good idea of how they formed. So I'm going to walk through the history. I like to do it in sort of 4 stages, because there are 4 really important geologic events that led to the formation of gorges like this one. And Robert H. Tremen is, in my opinion, the best park to show it for a few reasons that I'll show you. So I have a general outline of what I want to do, but if you have any questions, let me know, and I will do my best to answer them. Most important process to forming a gorge is first you have to have the rock. And so this particular rock is about 370 million years old, which is a really, really big number, and it's very hard to wrap your heads around. It's about twice as old as the dinosaurs. So this is before there was vertebrate life on the land. This is the Upper Devonian. It's also known as the Age of Fishes. And most complex life was still in the water at this time. So you had plants on land, but that's about it. And so these rocks were forming at the bottom of a shallow inland sea. So you can imagine where we're standing right now would have been below thousands of feet of water. And not only that, it's oceanic, so it's marine water, it's salty. And it's actually tropical. So hopefully you all know that the continents move through the course of geologic time. You know, they move at about the rate that your fingernails grow. And so at this time, central New York was located just south of the equator. So it was nice and warm, and one of the things that illustrates that, unfortunately not in this gorge, is that we have beautiful coral reefs that grow in rock of this time in central New York. So it's probably lucky for the park that there aren't fossils here, because you're not allowed to collect in state parks, so they don't run that risk. But we also don't get a look at any today, which is too bad. But we have some really beautiful evidence that this was once underwater, because if you look up here, we have these perfect ripple marks, and they run all along here. And those are either from being relatively near to the shore, so they're just normal tidal ripples, or it could be from storm surges. Storm surges usually have a much longer wavelength than this, so this is probably represents a near-shore environment. And so obviously we need a source of sediment in order to get these layers and layers and layers of what, when it was forming, was essentially mud. And so way off to the east, roughly where the Appalachian Mountains are today, were these huge, like Himalayan-sized mountains called the Acadian Mountains. And off of these mountains, you know, there were rivers and everything, and huge deltas got built out. And so sediment would be washed off of these mountains and sort of like filter down to the bottom of the sea. And that's what this is. This is mud from those mountains, you know, miles and miles off to the east. And so there are 2 interesting processes going on, which is why you get this interesting cycling from sort of more thickly bedded things to very thinly bedded things and back to thick again. And it sort of repeats over and over. It's not terribly regular, but it's frequent at least. And so these probably represent changes in water depth. And so the closer to the mountains you get, the bigger grains of sediment that you can have being washed off the mountains. If you're right beside the mountains and there's a river rushing down, you know, it can carry some pretty big, at least sand grains and that sort of thing. And so as sediment got washed out, deltas were getting built up. So the shoreline was moving towards us. And so as the shoreline's moving towards us, we go from very fine grain, the really tiny, tiny mud, that's all that can make it out, and then you start to get thicker and thicker stuff, which gets to be even a little bit sandy here. It doesn't sound like much, but sand is much bigger particles than mud. And so this probably represents a pretty near shore environment close to that delta. But then you have another process that's going on where when you have big mountains, the weight of them sinks into the mantle below a little bit. And so all the area around it, which is where Ithaca would have been. So imagine this is the mountain range, and this is where Ithaca is. The weight of it going down is pulling down the surrounding area where we are. So that's first of all why it's flooded. But as it gets pulled down, then the delta gets submerged beneath the ocean again, and then you're back to this fine-grained mud because the shore is so far away again. So you get these cycles, and this is over millions of years. So these are very long-term cycles, but you have them all represented here very nicely, especially with these nice ripples that show you that we're getting pretty close to the shoreline right here. So the first major step to forming a gorge is you form the rock. So there you have the formation of the rock. Really, we have mud first. So this process was going on for almost 100 million years. So as it was going down, this was getting deeper and deeper below the surface. So of course there's more and more mud getting piled on up at the top and even beyond what's here today. So as we'll see as we continue the tour, there was much more rock above what we have today. That's how it got sort of compacted and squished into the rock we have right now. All right. Any questions? Okay. So, step one, we make the rock. Now we've got the rock, right? It's funny, when I take people through here, they're usually aware that many of the state parks were built by the Civil Corps of Engineers in like the 30s and 40s as part of the New Deal. And so they're like, I wonder why they cut such straight channels through the rock here. And it is like laser beam straight. You can see they're like really flat, straight sides, and they continue all the way to the other side, all the way through the park. So it kind of makes sense that, you know, if you don't know any better, like, why would there be perfectly straight sides? Well, clearly somebody cut it. Of course, that's not the case. Why would they continue to cut up into the wall like that? So what actually happened was about 240 million years ago. So now there are dinosaurs around. So this is like a little more than 100 million years after the rock initially formed. And remember, it's going to be buried beneath. So before we were imagining that we were beneath a shallow sea. Now imagine we're beneath thousands of feet of rock, younger rock above us. So all of this pressure is what formed the rocks, but also helped lead to what cracked the rocks. So if you are a structural geologist, you can sort of think of the history of the Earth as a series of bumper car matches between the continents. They're constantly moving apart and then colliding together again. And so remember I said there were these huge mountains that were off to the east, roughly where the Appalachians are today. So about 240 million years ago, North America collided with what's called Gondwana. So Gondwana is South America and Africa and other bits of other continents that was around just before Pangea. And so it came over and sort of collided with North America, and that is actually the formation of Pangea, which if anybody is familiar with any supercontinent in the past, it's Pangea, because that's the one the dinosaurs lived in. So when this happened, it was this huge catastrophic collision in super, super slow-mo. The same sort of collision is happening right now with India running into Asia. And so you have these two continents, and they're sort of crumpling into each other. And this is called an orogeny. So it's a mountain building event. And so this mountain building event was going on off to the east and was actually the last phase of the building of the Appalachians. So it's called the Alleghenian orogeny, but some people call it the Appalachian orogeny because that's how we got the Appalachian Mountains. So this pressure of Western Africa colliding with North America created the mountains, but we're a ways from the mountains. And remember, this is very deep down, and so rather than buckling, this cracked in very straight lines, and there are two sets of them. So there's this set that the water's running through right now, and then there's a set that goes almost 90 degrees to it, which you can see the face of basically everywhere you look. It makes almost perfect squares everywhere. It's like 88 degrees off of, 88 degrees. So if you're a structural geologist, you can use these angles, and you can figure out about where the maximum pressure from this collision was when it happened. It turns out that Africa ran into North America a little wise off of where Long Island is today. And so these cracks are propagated throughout New York. You can go to Taganic State Park, you can go up near Albany, and you'll see cracks that are similar, and they all sort of like point to Long Island, which is roughly where Africa hit us, right? So these cracks were not here because engineers cut them, but if you get an aerial view and you look down, especially in Taganic and this gorge here at Tremen, you get this cool lightning bolt pattern because they zigzag through the landscape because the water is, of course, following the path of least resistance. So if you have a big crack there, and you have a big wall here, it's going to go through the crack, obviously. Okay, any questions about that?
It's crazy how straight it is.
It is crazy. That's not a question. And this is also a really great place because you can see, so this is a little bit misleading, but down here are some ripple marks, but there's a little bit of calcite in this rock too, and so you get sort of little potholes in it. So the rain is naturally slightly acidic, so it really exaggerates the little divots there.
What's the source of the water in our gorges? Like, where is it flowing from?
It's all rainwater.
So there's no lake above us that's...
Nope, there isn't. But as I'm sure you know, they all flow into a lake.
So how long did it take to form the cracks? Like, so the collision happened slowly over time?
Right. So the orogeny was happening for about 50 million years. So it's a pretty long-term event going on. And so I'm not sure how well constrained the actual cracks are, if they were forming during that entire time. But certainly, once they formed, they would get worse and worse as there was more pressure. And to sort of give away part of the ending of the story a little bit, when the glaciers retreated from this area much, much, much later, the release of pressure has actually caused these to move a little bit too. And so there's constantly tiny, tiny micro earthquakes that we can't feel, but every once in a while we'll get one that is noticeable, and that's because of this release of pressure that happened, merely 10,000 years ago. And so it's slowly sort of easing back up from the weight of the ice. Okay, so that brings me to the next chapter. And if you're getting bored, don't worry. There are 4 chapters, but the last 2 are much shorter. So, where we left off, we were under a ton of rock, right? So, where did all that rock go? This rock is 370 million years old. Clearly, there still would have been more rock forming after that. So, the answer, of course, as hopefully everybody in the area knows, that this was glaciated. So, starting about 32 million years ago, the Earth entered what sometimes is called an ice house climate. So for most of the history of the planet, there are no polar ice caps anywhere on Earth. But occasionally, it will get kicked into what's called an ice house climate, and you'll start to get ice forming at the poles. So 32 million years ago, for whatever reason, ice started forming on Antarctica. And part of the reason is that there's a continent that moves over a pole, so there's something to sort of catch the snow when it falls. If it falls into ocean water, there are currents to keep it warm, plus it's salty, so it needs to be much colder in order to freeze. So if you have land for it to fall onto, it can it's much easier for the snow to persist all summer long. And the other thing that scientists think was going on 32 million years ago that started this ice house situation is India crashing into Asia. And the reason they think that helped kick us into an ice house is because all of this new rock that had been buried for so long suddenly gets exposed to the air, and part of the weathering process is that you have all of these metals and various minerals that bind with carbon that's naturally in the atmosphere. So all of these rocks are sucking the carbon out of the atmosphere, and so that's reducing the number of greenhouse gases and drops the temperature. There's ice forming on Antarctica, and once you have ice, then you create sort of a little pocket of cold that never goes away. Plus, the ice is white, and so it's reflecting more of the sun's heat back into space. And so you have all these feedbacks, and so it starts to get cold and colder and colder and colder, and then till just very recently, only 2.5 million years ago, ice started to form in the northern hemisphere. And that's what colloquially is known as the Ice Age. And so the Ice Age is when glaciers started to form on Greenland, North America, and parts of Europe and Siberia. And so for the last 2.5 million years, there have been these huge ice sheets moving from the north and spreading down halfway over the United States, down to Kansas at their maximum extent. And these are governed by astronomical forces. And so, this is 2.5 million years, and at least at first, these seem to be governed by 40,000-year cycles. And so, based on the rate of these cycles, scientists think that we have maybe right here where this gorge is, there was miles of ice above us, like dozens of times. Like at least 30 times, ice has come down from Canada, basically, and scraped off all of the rock that would have been above us. So that's how all this rock got exposed. And it's interesting because a glacier leaves a lot of evidence behind. First of all, it smashes all of the rocks that are there. That's a pretty good clue. It leaves all of these rocks that don't really belong here, which is another great clue. So we have all kinds of rocks, especially if you're a farmer and you're plowing your field, you'll get all of these like pink granite boulders that you don't look like anything else for hundreds of miles around. It's because the ice picked it up as it was scraping through Canada and dragged it all the way here. Sometimes 200 miles from Canada, and when it melted, it dropped all the sediment here. So that's why we have all these weird boulders and stuff that don't seem to belong. Okay, so that's the glacier part of the story. Are there any questions about that?
When's the last time this area was covered in glaciers?
Oh, that's a really good question. Okay, so the last time the area around Ithaca was covered was about 18,000 years ago. And so I was talking about the sort of periodicity of these glaciers. So they would, build up, and then the climate would shift just enough so that, they're still moving southward, but they're melting faster than they can maintain with, more snowfall. And so the most recent one, the maximum extent was about 20,000 years ago, and then it started to retreat and was totally out of the area by 12,000 years ago. But 20,000 years ago, there were 2 miles of ice above Ithaca, which is really hard to imagine. That's more than there was, of the water it's really hard to imagine. We don't have any skyscrapers to really compare against, so it's kind of hard to wrap your head around. So the interesting thing about the most recent glacial advance is that so there were already stream valleys. So the most recent time that the glaciers weren't here before now, there were river valleys flowing north-south. And so when the glacier returned, of course, it's going to go to the lowest point. So it's following these river valleys. And so, and you can kind of imagine glaciers as like a conveyor belt. They're constantly scraping, even if the front is not moving very quickly. The ice, you know, in geologic terms, is moving rather quickly. And it's dragging all this sediment and stuff. So it's like sandpaper constantly being rubbed over the landscape. And so, where it flowed into these river valleys, it gouged really, really deeply. And so when finally the glaciers then retreated, there were these huge like chasms left in the landscape. But of course the ice was melting, so they immediately got filled with water, and that's how the Finger Lakes got formed. And actually, so does anybody know how deep Cayuga Lake is? You should know. It's a little over 400 feet deep. And so that's pretty deep for a lake that isn't even a mile wide. But when you get to the bottom of Cayuga Lake, you hit sediment. And the sediment is all stuff that's, you know, been washed in since, like, as the glaciers were retreating and since then. So to go from the sediment down to the bedrock, which is what the glacier was scraping, is 600 more feet. So they were more than twice as deep when they formed. Okay, so now I'm getting into the last part of the story. Okay, so imagine there are these huge chasms in the landscape of New York, and there's a kind of a lake at the bottom, because remember, they're more than twice as deep at that time. And so all of these rivers are flowing where there used to be ice. So you have all of these new rivers coming in, and they're just basically flowing and then dumping straight into this lake that's really far below. It's called a hanging valley. So imagine like this bridge is where the lake is. All of the rivers were flowing over the top and just dumping straight in. So at this time, when the last glacier left, there aren't any gorges yet. So people always think that, you know, the gorges have something to do with the glaciers. They do, but when the last glacier was here, there weren't any gorges. It's because it's all of these rivers that were dumping straight into the lake have been slowly eroding backwards towards their sources and eroding all of the rock in between and dumping it in the lake. So that's why the lake is half as deep as it used to be. And it's also why we have this huge volume of rock that's just missing. So this used to be a hill, and then this little stream washed it all into the lake. And especially when I take kids in here, they don't believe me, but last summer we had catastrophic flooding, which is why this place is closed right now. It's because it can wash huge boulders down, and of course the rock is already cracked. And so it actually doesn't take, you know, a 100-year flood to wash a ton of sediment down this gorge. It's actually a pretty rapid process. And it's not really, it's maybe hyperbolic to say that, you know, this little stream formed this entire gorge in the last 10,000 years. That's extremely rapid on the scale of geologic time. And remember I said that glaciers have come through many, many times to this area. And so you can see evidence of past gorges. So if you go down to the lower part of this park, you can see a gorge wall like this, but part of it is full of sediment. And that's where a gorge used to be, and then another glacier came and dumped a bunch of sediment into it. So you can imagine in, 90,000 years, I guess, when the next glacier comes through, you know, if it does, it'll fill this up with all the sediment it's carrying, right? And so then when it melts away again, the water has a huge head start because it just has to wash all the sediment out of the way, not bedrock like the walls. And so...
And will that then fill the lake even more?
Yeah, yeah. Although, presumably, the glacier will follow the lake again because it's still the lowest point in the area and gouge a bunch of stuff out of the way. So
The lake will get bigger.
It'll probably get wider and deeper for a while, but then fill up, and eventually it'll be, after a long, long time, it'll be very, very full of sediment.
So like all of it could be underwater.
Well, it'll be under ice first.
Right, eventually. Like downtown it'll be underwater, like Cornell and Ithaca would like survive up top.
Maybe for a while anyway. Yeah, it's interesting because you notice the topography of Ithaca as a town. It has the 3 hills, and then downtown is quite flat. But I mean, not that we have enough population to build big buildings, but even if we did, we couldn't build big buildings for the same reason that Manhattan can only build tall buildings in certain parts. It's because downtown Ithaca is all sediment. So there, beneath downtown Ithaca are about 300 feet of glacial sediment that's been either washed down a gorge and dumped at the foot of the lake, or was left there. Actually, it according to glaciologists, of which I am not, there's a moraine right at the end of Ithaca. So sort of the glacier came down and then stopped, and obviously the ice is still moving, just the margin isn't. So it's just bringing new sediment down, but not moving relative to the landscape. And so it just dumps a pile of rock there. And so that's sort of the end of Ithaca. And then the rest got filled in with sediment after it melted.
Where's the end of Ithaca?
Around the base of South Hill.
Is that how the hills formed there, or were those?
Most of the hills are bedrock, but there are moraine hills. So the Ithaca one, there's a series of them. There's one that's at the very southern part of Ithaca, and then there's one just north of Spencer. There are others in the region, but there are also drumlins, which are formed when so the ice is coming along and there's some sort of barrier, so like a big boulder that it got caught on something or whatever, and so the ice is going along and then it gets sort of blocked this and has to flow around it, and then there's like a shadow behind it. There's like a shadow behind it where the ice is just dropping sediment but not scraping because this boulder is protecting it. So the ice is coming across and just dumping sediment right behind whatever the obstruction is. And it makes these really cool teardrop-shaped hills all over the landscape. And you can find, they're called drumlin fields, and they're just all over the place. In fact, there's a golf course called Drumlin just south of Syracuse, because it's on a bunch of these hills. And not only are there a whole bunch of cool teardrop-shaped hills, they all point the same direction, which is exactly the direction of flow of the glacier.
So then what happens to whatever was blocking it? Does that become the front of the hill, or does that...
It either becomes the front of the hill, or it erodes after the glacier is gone. So, yeah.
So these are carved by the water after the glaciers, not by the actual ice.
That's right, yeah.
But you said they were carved by rivers?
Well...
By rivers coming from a source or from rainwater? I'm still confused about that issue.
So the existing valleys that were there before the glacier last came through, I don't know.
Okay. It's rainwater.
Yeah, it's presumably rainwater. And they were actually flowing from the south to the north, which is weird because it's flowing towards the glacier. So I'm not really... It could be that... remember I was talking about how these cracks were sort of reactivated when the glacier left because the release and pressure has caused them to move a little bit again. So it could be that when the glacier retreated, sort of the north, Canada, was still depressed from the weight of the ice, but here in Ithaca, it wasn't, so it sort of sprung up, and then that's why it was flowing northwards. So then when the glacier advanced again, it was kind of going up the valley.
Cool.
All right, the end.
Thank you. Thank you.
How do I turn it off?
Here, I'll turn it off. Thank you, Alex. It was awesome.
My pleasure.